Okay, so we're going to start. So this week we're looking at object-oriented programming, which I'm assuming everyone here has already done some object-oriented programming before, so people know, at least for high level, of what we're going to be talking about. Today's and this week's stuff is quite technical in terms of C++ and some memory management and how it is organized and how it runs. Also, this week, hopefully, provided we get through all this, is the last week of content that will be in the exam. Next week, we'll be focusing on more practical C++ libraries and stuff like that. So next Monday, provided we get through all the object-oriented code, I'm going to present some stuff on how you can do basically some high-speed performance or things to think about when designing programs that might actually help with assignment 4 in terms of thinking about containers. I might also talk about assignment 3 and how I managed to get it going very fast. Again, if we have time, Sean might give an overview of how the Robocup codebase is structured and the considerations they need to make there in terms of performance and getting high speed out of C++ in that regard. And then on Thursday next week, we've got Dave, who's one of the other tutors, giving a guest lecture on Boost and some event-driven programming and callbacks and other stuff that you might find that you need to do when working with large software projects. Okay, but that's next week. And then also for week after, on the Monday, like I've already told you, there's a lecture on the Monday of week 13, which is the 2-hour revision lecture. Okay, so let's get into it. So object-oriented programming. There's 3 things that we're going to talk about this week. We're going to be talking about inheritance, we're going to be talking about polymorphism, and we're going to be talking about dynamic binding. Now, inheritance, if you've done any OO before, should be straightforward. It's whereabouts you have a class that extends or inherits from another class. So you might have a person, and you might be able to extend that person, say, to a staff member, or they're a student, or they're a parent, or they're an adult, or a child. Polymorphism is whereabouts we can have an object of a particular class be used if they're an object of another class. The people example comes back. A child might be able to do the same, or should be able to do the same functions as a person. So a person might have the function talk, and a child should be able to talk, and an adult should be able to talk, and so they can share that functionality. And that polymorphism is something that's shared from base classes down to inherited classes. Then we have the idea of dynamic binding. And dynamic binding is runtime resolution of appropriate function to invoke based on the type of object. This means that when we have, again, this inheritance, this hierarchy, dynamic binding allows us to say we have a function called talk, and it's defined for a person, it's also defined for a child. The child version overrides or masks the person version, and the child version of talk might put on a child's accent or might reduce the vocabulary that's available to the child or something like that. If we treat the child object as a child object, then when we call talk, it will call that child version of the function talk. If we treat that child as an adult, depending on our code, okay, this very much depends on our code, it may invoke the person version of that talk function. Okay? So we've got 3 things we're going to look at: inheritance, polymorphism, dynamic binding. All these things are related to each other. And inheritance, and to a degree polymorphism, I expect you to already know. But let's look at inheritance to start with, okay? And a lot of this object-oriented programming paradigm that we're going to talk about is talking about how to, again, solve problems, how it can represent problems in a way that allows our code to be broken down into small chunks. That's the whole idea of object-oriented programming. So if we can split the program down to small chunks, we can work on certain sections of our code at a particular time, and we can also have better encapsulation of how we achieve things. And so encapsulation, again, principles of OO, you might have a table here. This table encapsulates some drawers down here, some content that is contained hidden within this table. There might be a relationship between the table and the screen, because the screen sits on top of the table, so there's some sort of interaction between the screen and the table. The table is encapsulated within the room. The room has some functionality: turn on the lights, turn on the projectors, open the door, close the door. Okay, so we break all our problems down into these little pieces. It makes our code easier to code. So we represent these concepts, these object concepts, as classes, which are templates for how to go and build objects. Relations between classes is often done through inheritance. And we untangle the dependency between classes by separating the interface of a class from its implementation. And so we go back to the person and the child. The interface in that situation is talk, because both a person, a child, or adult talks, so the interface is talk. The implementation might be different between a child and an adult. Okay, that should be revision. So let's look at how we do this in C++, how we do inheritance in C++. Okay, imagine we've got a bookstore, and a bookstore stores some books, and there can be different types of books. It can just be normal books which are undiscounted, just normal prices. We can have a discounted book, and that's the same as a normal book, only it's got a cheaper price. And we can have a used book. And a used book is still a book, but because it's used, it might be in a different condition. A used book is often a little bit older, a little bit worn, and often it's also cheaper. A used book is often cheaper, even on a discounted book. And so we can go and create this book class that represents a book. It's got a title, a name, contents, ISBN number, price. Okay, we've actually already seen this book class, about week 3 and 4 of the semester when we're looking at operator overloading. Okay, so a lot of these slides will relate back to stuff that was very early on in the semester. So we've got a book class. We've already seen it. We can then have a discounted book class, and we can have a used book class. If we say class diskbook public book, that is C++'s way of inheriting. It's the same as extends in Java. Class diskbook public book, okay, is saying to the compiler, saying to the C++ compiler, create me a class diskbook that extends, inherits from book. And so you have a class hierarchy. Okay, now if this was UML, those arrows would be slightly different, but it's not. Okay, so we've got a discount book class, we've got a used book class. Both of them inherit from book. Okay, this is what then the code might actually look like from a base class. Okay, so the normal book class. Class book. Okay, yes. Take a look at the public stuff. We have a constructor, okay? Constructor takes in some default values if you don't supply them as well, okay? We have a function called ISBN, which returns the ISBN number of a book. We have this function called net price, okay, which returns the number of books that we want to buy times the price of an individual item. And we have a destructor. We have an ISBN number, which is a string. We'd probably, in this book, of course, also want to store the name and other bits and pieces of this book, but we don't for this example. And we have a price. We have a price. Now, there's some new things, or there might be some new things on the slide that you haven't seen before, but hopefully we should be able to work it out pretty quickly. Okay, so the first one we've got is public, private, and protected. What does public mean? Publicly, what does it mean by publicly available? What can you do with it?
Other objects that have access to an object can use the public interface.
Okay, anything that's public, anything else can access. What does access mean? What can they do with anything that's public? They can read and they can write to it. They can read and they can write to it. Okay, and that's why in good object-oriented design, we do not make our fields, our variables, public. We make them private, and then we have getters and setters, which are public. And in some situations, we only want for getters to be public, and we can make for getters public, which means that people can read for data, but they can't write for data. Now, it should be obvious, but what does private mean? Now, it's not just non-public. What does private mean?
Only accessible within that class.
Okay. So private means only accessible within that class, correct? What happens if I have a public method in a class, can they access the private data of that class?
Yes.
Why?
Because it's in that class.
Because it's in that class, yes. So even though a method might be public, it can access the private data members of the same class because it's in that same class. Now, what does protected mean?
Classes that inherit from this class can access this field.
Okay, so protected means basically that. Classes that inherit from this class can access, and by access we mean read and write, this field. So inherited classes can access and read and write this field. But to anything else that doesn't inherit from this class, it's the same as being private. Okay? So our discounted books, used books that are about to inherit from this class can access that protected data. Okay? But anything outside that class can't access it. Okay? An inherited class cannot access the private data members of the class that it inherits from. Okay, so anything that's private in a class, even inherited classes cannot access the private data members. Peter.
If you have a public setup for a field, why not just make the field public?
If you have a public setup for a field, why not just make the field public? That's more of an OO question than a C++ question. Okay, it's basically design convention. Okay, you can have a public setup for a field, and that public setup for a field might do more than just setting the variable. It might check that the value is valid within a range. It might do some other checks before setting that value. If you just make that value public to everyone and don't have that setter that wraps around it, it means that anything can go put some data into there and you don't know if that data in there is correct. So your setter, your public setter, might be more than just setting the value. It might do some checks to make sure that it's conforming correctly into the right data required for that field. Okay. Okay, so let's continue talking about the base class. Okay, so when we talk about an interface in Java and an interface in C++ are a little bit different. An interface in Java is a particular type. Type's probably not the right word, but a type of file that defines an interface of things that a class must define. An interface in C++ means it's all its public members of a class is its interface. Private and protected members are inaccessible in user code. And also there are two types of functions. Okay, let me go back a slide. The thing that we didn't talk about is this keyword virtual that showed up. If we look closely, the constructor and this method called ISBN are normal. They're what we've seen before. This keyword virtual showed up on the function netPrice and also on the destructor. Okay? Virtual is very, very, very important. First of all, the keyword virtual needs to be put in front of any method for it to be virtual. What it does is it turns on dynamic binding. Virtual turns on dynamic binding. That dynamic binding is that ability for, say, go back to our person and our child. That dynamic binding is for child to be able to call that talk method and call the child's version, or to be able to call the adult's version when it's being treated as an adult. Okay? When you say something is virtual, you expect it to be overwritten by the inherited class. When something is virtual, you expect it to be overwritten by the class that's inheriting it. Non-virtuals have static binding. That means at runtime we cannot change which thing is going to be called. And it's expected to be inherited by the derived class. What that means is a non-virtual, it inherits the function and doesn't change it. It can just call it, inherits it. With something being virtual, it's expected to be overwritten, to be replaced with an updated version of it. Virtual destructors are really important, and we're going to talk about them either later on today or otherwise on Thursday. So here's our derived class. Okay, so we had our base class. Here's our discounted class. A discounted class inherits from public book, but in the declaration we then redefine net price. Okay, and we keep the word virtual on top of it, but we redefine that one. And our private data, we now have this minimum quantity, and we have this discount. And so when we call this net price function, our previous net price function, which is up on the right-hand screen, just called n times price. Okay, just calculated what the price of something was. This overridden net price function says if n is greater or equal to some minimum quantity, okay, so we might give a discount if people buy a whole lot of stuff in bulk, okay, then return whatever the discount is, okay, so the discount might be a certain percentage, okay, so say 20%, so 0.2. 1 minus 0.2 is 0.8, so n times price times 0.8, okay, so we give a 20% discount. If we hadn't have written virtual at that point, the code would not behave how we expect the code to behave. And we're going to come back to that later on today. Okay, so this virtual keyword's important. Okay. Now, when we do inheritance, notice the word public up in front of here. Okay? We're doing a thing called public inheritance. And it's almost completely universally used. This is what everyone does. Okay? And like I stated a few minutes ago, it means that all the public and protected members are inherited as if they were declared in that derived class. Okay? Public members remain public. Protected members in an inherited class through public inheritance remain protected. Okay? That means that we can have a cascading effect of inheritance. We can have so I can have a person. A person is then inherited by a class called child. Child is then inherited by a class called pre-teenager or preteen. And those protected members will flow through. Okay? This is also known as interface inheritance for a reason that's simply that the public functions are the public interface. Okay, like we said, it's the equivalence of extends in Java. Name hiding causes exceptions to the rule, okay, and we'll talk about this either today or otherwise Thursday. So basically, if you don't inherit something, or if you don't override something that should have been overridden, you can end up accidentally hiding some functionality. Okay, if you want to do private or protected inheritance, change the word public out for private or protected. Okay. The slide here says we'll discuss this later. We probably won't because it's not in the exam. Also, really important, friendship is not inherited. Friendship is not inherited. So friendship is only with the class that gets defined as being a friend. Okay. So if I have a class bookstore, and bookstore is friends with the class book. It is not friends with the class discounted book. The class discounted book would also need to be defined as a friend of bookstore. Okay? So friendship is not inherited. And there's a question on that in for tutorials this week. Okay? Yep.
So I've made a class that extended book,
Yep.
and I didn't implement the net price method.
Yep.
And then I called net price
Yep.
on that class.
Yep.
Would there be a...
No, if the question is this, if I had net price is virtual, okay, so function net price is virtual, and your question is, if I inherited from book, didn't overwrite net price, what would happen? Your code will be fine. We're going to come to this in a few minutes time. Okay, your code will be fine. It will use the previous one. Okay, but something being virtual, the idea is it always gets overridden. Okay, and we're going to come to this. Okay, so hang on. I'm not sure if it's in this first hour or if it's in the next hour, but we are going to come to this point. Okay. So, and we've already seen this. This is just revision again. We break our class down to public things, protected things, private things, and through this we basically support encapsulation. And also, friends are part of the public interface. Friends are part of the public interface. And friends can also access all public, all private, and all protected data members. Now, let's talk a little bit more about protected. So, a derived object, it is an inherited object, may access the protected members of its base class only through a derived object. Okay, so if we have the book being the base class, and we have the discounted book being the derived class or the inherited class, we also have a separate class being used book that also inherits from book. Okay, we can inherit through those protected members. Okay, here's another example. We have a class called ABC Phone. Okay, the class called ABC Phone has a function called ring. That's protected. It's also got a protected data field called secret. Okay, so we have a class, base class called ABC Phone. It's got a protected function and a protected field. We then say class PhoneMaker1 inherits public ABC Phone. Okay, that means because we're doing public inheritance, PhoneMaker1 has access to ring and to secret. Okay. We then say class PhoneMaker2 also inherits public ABC Phone. We've got this void function f that takes in a PhoneMaker1 object, and we call p, okay, so that's a pointer p pointing to ring on that, and also we try to print out p pointing to secret. Now the question is, does this code compile? Who thinks this code compiles? People are scared to put their hands up. Who thinks it doesn't compile? About 2 people. Who doesn't know? Why do you think it doesn't compile?
Because public PhoneMaker 2
Yep.
is accessing a PhoneMaker 1,
Yep.
not a phone, and it's protected only for the one layer.
So PhoneMaker 1 has inherited ABC Phone. PhoneMaker 2 has also inherited ABC Phone, but a PhoneMaker 1 and a PhoneMaker 2 are different objects. Okay? So even though PhoneMaker 1 takes in this pointer to this PhoneMaker 1 object, so P is this pointer to this PhoneMaker 1 object, inside the class PhoneMaker 2 it can't use P pointing to ring because, as you correctly point out, that belongs to that class, it's protected, we're outside of that class, Okay, we're in a different class, so it's not going to compile. Okay, and I have an example, I hope. If I go find phone, just make sure it's the right one. Yep, okay. So, if I try and compile this, okay, unfortunately there's no makefile for this week, so you're just going to have to bear with me typing. G++, standard C++11. If I try to compile phone.cpp. Okay, in function void phonemaker2, ring is protected. There you go, so it doesn't compile. So both ring is protected, secrets protected, okay, so none of that works. Of course, I can make this work by changing that from a 1 to a 2, okay, and now I'm within the same class, and now that compiles fine. Okay, so that version on the left-hand side doesn't compile, this version on the right-hand side does, although the one on the right-hand side doesn't do what you expect it to do, because that one's now taking a phonemaker2 object rather than a phonemaker1 object. If I wanted to make the phonemaker1 object, actually that code work, what would I need to do?
Take an ABC phone.
Oh, take an ABC phone, let's see. This may work. I think this will work. Yeah, it should work. Okay, doesn't work. I learned something. It's protected within this. Okay, yep. The reason why it doesn't work. Who thought it would work, by the way? Who thought it didn't? It wouldn't. Why do you think it wouldn't? Like I've got the explanation, but why wouldn't it work?
So it might be the same solution as the phonemaker one.
Yeah, it's going to be the same situation as before. This ABC phone, you can't guarantee isn't a phonemaker 1 in disguise, just as an ABC phone. So within phonemaker 2, even though it extends ABC phone, and even though we can say phonemaker 2 is an ABC phone, phonemaker 2 cannot access protected data members of ABC phone object by itself because it is a different class. Okay? So no, that doesn't work. Okay? So that doesn't work. There is another way to make this work, okay, but it's dumb. It's just go make in ABC phone that public, and that stuff will work now. Okay? But that defeats the purpose. Okay? Sorry? Make them friends. Making them friends, that might work. Okay, so where am I going to make them friends? Am I going to do this? Is that the solution? Who thinks that's the solution? Anyone? No? Why is that not the solution? Correct. So that's the solution. Yep, you think it is? Okay, let me just fix up this bracing. So what do you think? Thank you. So that should work now. And it does. Okay? So, yeah, making them friends fixes that problem. Okay, so there's a couple of different solutions to how we fix that, but see, this gets into a little bit of a complex situation straight away.
Doesn't that mean every time you extend ABC phone, you have to make them all friends with each other?
Yeah, exactly. If every version that you extend, if you want to do this function, you'd have to make them friends with each other. It becomes an awful mess pretty quickly. So you'd probably want to make, say, for ring function public or something like that. It depends on what you're designing. Toy examples you can have lots of problems with. Okay? If you had a situation about they all need to be friends with each other, there's probably something broken in your architecture. And you probably need to think about how to fix that. Why don't we put for F function in ABC phone?
So if it's going to be the same,
Well, it depends. It depends on what you're trying to solve. Okay, two examples aren't going to cover off every single situation. It depends what you want to solve. If your function F, your void F, okay, wanted to work for any ABC phone, yeah, that's the solution. But what happens if it didn't? What happens if it only wanted to work for phone maker 1? Then your solution is to make it a friend. So it depends on what you're trying to solve. Okay, so let's talk about relationships. Now, relationships, this is just terminology, okay? There's lots of different ways of saying the same thing. So we can talk about the relationship between book and discounted book as being a discounted book is a kind of a book. It's derived from a book. It's a specialized form of the book. It's a subclass of a book, or it's a derived class of a book. And then we can say in reverse, a book is the base class of a discounted book, or is a superclass of a discounted book. We can also say that a disc book is a book, okay? But we can't, so we can say for every discounted book, it is a book, but we cannot say that for every book is a discounted book. You can't go in reverse, okay? And that's what that last point says. You can use a discounted book where a book is expected, but not vice versa. Okay, and we're going to come back to this when we start talking about memory. The same works, okay, here's a person example. In this case, we've got a student and a lecturer, okay, but a student extends a person, a lecturer extends a person. A student is a kind of a person, yada, 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 but we cannot say a student is a lecturer. We can say a student's a person, we can say a lecturer is a person. We cannot say a student is a lecturer. That doesn't make sense. Okay? So, who has not done Java? Anyone not done Java? Oh, one person. Okay. So I'm going to make a lot of comparisons to Java because a lot of people have done Java before they did C++, particularly for object-oriented stuff. If you're coming from Java, all methods in Java are virtual. We don't put the virtual keyword everywhere because all methods in Java are virtual. We can inherit of any class and we can override any function. Okay? In C++, there are two differences in the functions. All functions default to be non-virtual. All functions default to be non-virtual. And then we have to manually make functions virtual using the virtual keyword. Okay, so there's a real big distinct difference between things that are virtual and things that are not virtual. C++ 11 also introduces the keyword final. And final is the same as final in Java. If you define something to be final, it means that it cannot be overridden. So if we say we have a base class, it's got a function called virtual void f. Okay, base class is called virtual void f. Okay, so this is f function can be overwritten in derived classes. We then have a derived class that inherits from base. That says void f final. We overwrite in the derived class that function f, but we say this is final. Anything that inherits from the derived class, okay, so anything inherits further from the derived class cannot overwrite that function. This is the final version of it. So if we have a second derived class, okay, so most derived inherits from derived, we cannot overwrite void f. It cannot be overridden. Okay? So final prevents something from being overridden. Okay, so let's talk about memory. We all clear up until this point because this is where it starts to go a bit harder. So all of this so far basically should have been revision with the exception of introducing the word virtual. Okay, we all clear up until this point? Okay. So we're going to talk about memory. and how things are structured in memory. Say we have a book object, okay? A book object has an ISBN number and a price, okay? Those are the fields of that class, and that's what gets stored in memory. The ISBN number was a string, and price is a double, okay? Which is there, okay? So on the right-hand screen, we've got, on the book, we've got the ISBN number and we've got the price. Okay, so that goes and gets stored off the memory. A discounted book object has an ISBN number and a price, and then it also has a minimum quantity and a discount. In memory, the book object and the discounted book object, they share the same memory layout to start with. So the top of this discounted book object in memory looks the same and is in the same object as that book object. The new pieces of this discounted book follow. Okay? So the first part of a discounted book object contains exactly the same as the book object, and the second part contains the new stuff in that order. Okay? Now, the reason for this, and we'll come and talk about construction and initialization again later on today, otherwise Thursday. When we construct an object, so we construct a discounted book object, when we construct an object, what happens is, the book's constructor is called first. Okay? So the book constructor gets called first, sets up the book object, and then the discounted book object, which extends that, gets called out second and extends it from there. Remember, again, this is revision of these parts. Only non-static members are stored inside objects. And, of course, the discounted book is more specialized and contains more information. Keep this in the back of your mind, okay? Because these next few slides are going to look at how these things all relate to each other. So let's look at the relationships between the base objects and the inherited objects. So a discounted book is a book, but not vice versa. Okay, what does it mean? We can upcast. We can cast from a derived book to a base book. Okay. So we first of all go and create a discounted book. Okay, DB. We can then create a pointer to that discounted book and install it as being a book pointer, because a discounted book is a book. We can also create a book reference and say the book reference is equal to that discounted book object, and that still works because, again, a discounted book is a book. But we can't downcast, at least not in this way. We can't create a book B and then create a pointer to a discounted book and assign it for address of B, because a book object is not a discounted book. Book object is not a discounted book. Same with a reference. You can't create a reference to a discounted book and assign it a book location. Okay? So you can upcast, but you can't downcast. Okay? Here's another example, at least with some casting. So we create the discounted book object. We then create a pointer to a book. We can assign it for memory address. That's fine because it's upcasting. We create a pointer to a discounted book. We can't assign for pointer Q is equal to a pointer P. We can't do that because it's still downcasting. Okay. We can do a static cast. We can say Q is equal to a static cast to a discounted book. Okay, this is a really bad idea, but you can do it as a static cast. Okay. You can also do this thing called a dynamic cast, okay, which will dynamically go and change it again. This is why casting is evil. One of these examples about casting is evil. Okay. Casting your pointers around like this, don't do it. If a reality is a discounted book is a book, but a book is not a discounted book, so you should not be casting something down. You shouldn't be getting your book class and trying to cast it into something it's not. Okay? Even though the later part of the slide will work, you should not do this. Okay? Casting is generally quite evil. If you have a book and you want to convert the book into a discounted book, you actually should just create a whole new object. Okay? Because this has got huge potential for error. What is one possible error this could have? If I have a book and I play with the pointers and make it through casting, think it's a discounted book, what's the potential error I could have?
You try and access one of the variables inside the discounted book.
Yep. Yep. So on my dynamically or statically casted pointer, I then try to call this net price function. My code is somehow going to do something nasty. If I get a segmentation fault, that'll be the best thing that could happen. Because the reality is this book object does not have a minimum quantity and does not have a discount. Best case scenario, I get a segmentation fault. Worst case scenario, the code goes and reads those extra bits and bytes that are after the end of the book object, thinking they're part of a discounted book object that's never been created. And my code goes and does something that I've got no idea what it could be. Best case, I get a segmentation fault. Worst case, I get some really bizarre, strangely undefined behavior I don't want. Okay? So don't do that. Now, these previous slides used pointers. We're now going to look at a thing called object slicing. So we're not going to use pointers. So if we create a discounted book, and we create a normal book and assign the normal book, so do a copy assignment of a discounted book, okay? Only the base part of the discounted book is copied. Okay, so again, these data structures up the top. If I do an assignment, of course, only the ISBN number and the price gets copied across. This is called object slicing. What I've literally done is I've sliced the bottom part of my object off, and I've lost it. Okay, I've lost it on that copy. So the discounted book, of course, will still contain the original thing, but this book B will have lost that data. Okay. So object slicing is a problem. We're going to come back to talking about object slicing, but object slicing is a problem. Also, containers and inheritance don't mix. Okay, if I create a multi-set, okay, so it's a container of books and they're in a basket. Okay, if I create book B and also discounted book DB, and I insert book B, that's fine. It inserts a copy of B, because when we insert into a container, it copies. When I insert discounted book, it copies in. It's a legal command. It copies in, it's fine. Only because it's copied into a container that's doing books with slice for object. And because of slice for object, we've lost that minimum quantity and a discount. Okay, so this is for object slicing problem. Okay, and it is a problem because we lose information and we're not aware that we're losing that information. Yep.
If we have a container of pointers,
Yep. That's fine. Because the container of pointers, why is the container of pointers not going to cause that object slicing problem? Well, no, it's still trying to insert to a fixed memory space, but it's trying to insert for pointer. It's copying a pointer, not for object. Okay? So if it's a container of pointers to books, it's fine, but you then have your casting problem from a previous slide. Okay? Okay, so here's a little bit of user code. Okay? Here's a little bit of user code, which we might tag onto the end of our book.cpp file, okay? It prints for total, okay? What it does is, let's go look at main first. We create a book, book 1. We then create a discounted book, DB. Also note that the constructor was not inherited. Okay, the constructor wasn't inherited. We then go and create this function called print total. Okay, this function print total is defined up here. It prints out the ISBN number. Okay, remember that the ISBN function was not virtual. Okay, so the base ISBN function always gets called. Then it prints out the net price. Now remember, the net price function is virtual, so it got inherited and overridden. Okay, so if we call it on the B object, it will call book net price. If we call it on the DB object, it will call discounted book net price. Okay, even though this print total, see, this print total is taking in this const book. It's taking in this const book. Okay, so this here is taking in a reference to book B, taking in a reference to book B. Okay, so we've taken in the reference to book B, and even though one of these things is a discounted book, because it's got the virtual, because it's been overwritten, it will call the correct function. Okay, I have this code on this right-hand screen. Let me just make it. Book.cpp. Okay, and so let's clear that. I run that, and I get a total price of 9.99. The second one, the number sold is equal to 10 because we're passing this size here. Okay, and because it had no default constructor, the total price is 0. Okay, but that called the second version. Okay, the way in which I can quickly show you this, if I just modify this net price to say standard cout book, standard NL, and we do the same down here on disk. Okay, and we remake this. Okay, the first one's a book, the second one's a discounted book. Okay, if I change in this print function, so instead of taking a reference, I take a copy. Okay, so call by value, and I recompile it, what's the output going to be? So this line up here, look on the left-hand side. I've changed this book B from being NB to being B. What is the output going to be now? Both are going to be called book. And they are. Okay, so that caused that object slicing problem. Having that reference didn't. Okay. Can I do this? Can I say const book disk underscore book? Is that going to work? Oops, let me just get the title of the class right. Is this going to work? So who thinks this code's going to compile? Anyone? Who doesn't think it's going to compile? Why not? Because I'm passing in a book. Okay, so I go to compile this, and bang, it doesn't compile. Gives me a whole invalid initialization. Doesn't work. Okay? Because I can't downcast. Okay. I'm going to stop for 5 minutes. Okay, so let's pick back up. So we've got this dynamic binding going on that we've just looked at, and how we've created this book object and we've created this discounted book object. And how we've called this print total function, and this print total function, it takes in a reference to a book. But because the net price function is inherited, the net price function for discounted book gets called. Okay, so we're going to break this down and take a look at the difference between static and dynamic binding. Okay? So something is declared static or something is static or, sorry, the static type or the declared type happens at the declaration. Okay? For dynamic type is the object in memory it's either pointed to or referenced. Okay? And so again, static binding happens at compile time, dynamic binding happens at runtime. Things that are declared virtual are dynamically bound at runtime. So, this here, let's take a look at this. We have a discounted book DB, okay? And so at compile time, okay, at compile time, we have a statically bound dynamic book, sorry, discounted book. We then have a pointer at static compile time to a book. So for object in the static binding thinks it's a book. It's statically bound to be a book. The same thing happens with a reference. It's statically bound to expect a book. However, at runtime, this dynamic object that's gone in is a discounted book object. So this dynamic binding works and basically goes, well, the discounted book is a book, so I can dynamically bound, or dynamically bind this book, this discounted book into thinking it's a book object. Okay, so at runtime, it's dynamically bound for this book object to be a book object. Okay. So again, the breakdown between C++ and Java, C++ and Java are both what we call statically typed. What we mean by statically typed is at compile time, every variable needs to have a type associated with it, and the type checking that goes on at compile time is this strict static type checking. We just saw that 5 minutes ago. We're about to change the print total. Instead of taking a book, it took in a disk book, and then attempted to feed a book object into it, and because of the static type checking, it happens at compile time, it said you can't do this. This is different from PHP or Python or Ruby or interpreted language that has dynamic typing, particularly JavaScript even. All these languages, you don't explicitly declare things to be ints or floats or doubles. Okay, those are what's called dynamic typing, and it works out at runtime what the type should be. Now, you can still get errors in dynamically typed languages, like particularly Python. Sometimes it will say something's a list or a string. We actually want it to be an int. You still need to do some degree of casting. Some other languages will start a particular variable off at a particular type, and then realizing that you're mixing it with a different type or it needs to be something else, and automatically do that type conversion for you. Okay, but coming back to it, C++ and Java, statically typed at compile time. Okay. In terms of the bindings, though, okay, so the bindings is binding this object to memory to this title of what this variable is and the type it's expecting. Okay, that binding, that memory binding, happens at runtime. Java, everything's dynamically bound. Everything in Java is dynamically bound because all functions are virtual. In C++, we have static binding for non-virtuals. And that's based on the static type of receiver. And then we have dynamic binding for virtuals. We've got things are virtual, they're dynamically bound. What this also means with the static binding for non-virtuals is the optimizer can come through and rearrange in terms of the memory where and how some of our static memory works and our statically bound memory works to basically make our code more efficient. Okay, it can stick stuff in interesting places, particularly if things aren't going to be written to anywhere in our code. So if we have it doesn't matter if we've got getters or setters, publics or privates. If we have a variable, in our code is A, never overwritten for inheritance, and B, always read after construction, never written to, even if we don't declare it as const. For optimize, it can still figure out, well, basically that's a const variable, and go and put it somewhere into memory to be a very fast lookup. Of course, you can't do that with dynamic binding because you never quite know if something's going to be changed or not. Okay? There's dynamically typed languages such as Smalltalk and APL. We're not going to talk about Smalltalk at all. And there's, programming languages courses, on the theoretical side about the pros and cons of these things. Okay? But just remember, static typing, that's required at compile time. For binding some objects in memory to the types happens at runtime, depending if they're statically bound or dynamically bound. Okay, which depends on if they're virtual or non-virtual. Okay, so this is for static binding for non-virtuals. Okay, so this is everything we've dealt with up until this point of the course. We have a book and we have a discounted book. We then attempt to assign a pointer for book to a discounted book object, and basically we try to do it first of all for a book object, and we try to do it secondly for discounted book object. Okay. Then what we attempt to do is, once we've done that assignment, we then attempt to call the ISBN function. Okay. Remembering that the ISBN function is not virtual, it was not overwritten. The ISBN function is part of the book, the base class. Okay? So the static type of P and Q, both the static types of P and Q are both book. Okay? So at compile time, that's a pointer to a book and that's a pointer to a book. Okay? And they're statically typed to be a book pointer. The static binding that goes on, because the ISBN function is not virtual, we'll call it to call book ISBN. The same applies in both situations because this thing is not virtual, and the same applies if these things are references. Okay, the same resolution happens. Okay, this is the easy one. Dynamic binding is more complex. If we have a discounted book, and we've got a pointer to a book, and we also have a pointer to a discounted book, if we just call the pointer to the book and pointer to the discounted book and call net price, okay, both of these calls will be made to the net price function defined in the discounted book. Okay, so let's go slowly through it. We have a discounted book object. Statically, okay, the static type of pointer PB is a book. Okay, so the static type of pointer PB is a book. The static type of PD is a discounted book. However, at runtime, they're dynamically bound to this discounted book object in memory, and therefore for call PB's net price, doesn't matter if it's for pointer to book or the pointer to discounted book objects, okay, it always calls for discounted book function for net price. Okay? If we're doing static typing, okay, so it didn't have, let's back this up. Sorry, static typing. So at compile time, what it thinks is going on, okay, is these calls. At compile time, this is the calls that it thinks are going on. Okay. At runtime, those dynamic bind resolutions work. And the function net price is said to be polymorphic because we can also create a pointer to a book, but assign a book object rather than discounted book, which is up the top, and call P pointing to net price, and I'll call book net price this time. Okay? And again, this can be done with references. Okay, so what's going on at compile time and what's going on at runtime is different. Okay, so this does get very confusing. You can probably see it umming and ahhing while trying to explain it, because this gets very confusing very quickly. Okay, what happens at compile time and what happens at runtime are different things. Okay, And this goes all the way back to, again, week 1, where we talked about, the very first lecture we said, what's the type? Actually, the answer's on the screen again, but if I go all the way back to week 1, I said, what is a type? What can you tell me? What is a type? What is the definition of a type? What can someone tell me? It's actually on the screen. What's the definition of type?
A set of values and a set of operations
Yeah.
for the values.
Yeah. But what does it mean? What does it mean? So for type int, what does it mean? What's the set of values associated with an int? Min value and max value. No, I've got a lot more than that. What? Can be any number. So can 3.14 be an int? No? Okay. So the set of values is the set of exact values that satisfy the type requirements. Okay. So for an int, it's a whole number. Okay. So it's a set of whole numbers correctly within a min value and a max value range. Okay. But what is the second part of that type? What is the second part of an int? What is the set of operations that can operate on it? Yeah, so you've got plus, minus, multiplication, division, modulo, all that sort of stuff. They're functions. They're also part of the type, okay? So the type is not just the values, it's the operations that can happen on it, it's the functions that can happen on it. In exactly the same way, a book has a set of values. The set of values in a book can actually be a set of book objects or discounted book objects, okay? The set of operations is for functions available on that particular class, okay? So when we extend to discounted book, the interface of book is still the same as before, okay? The interface has stayed the same. The set of operations available on discounted book, if we don't put any other operations in, the set of operations on discounted book is the same set of operations as on book itself. But the implementation, the definition can be changed in discounted book, okay? So these are then called polymorphic types, okay? Polymorphic types are types that work with virtual functions, okay? So polymorphic types are types that work with virtual functions, but static typing continues to work. Okay, this is important to how the compiler works. Okay. Now, we can have what's called pure virtual functions. Okay, and pure virtual functions lead to the notion of abstract base classes. Okay. A class is an abstract base class, or an abstract class, if it contains some pure functions, okay? Well, I say an abstract base class is something that contains some pure virtual functions, okay? It'll be declared or inherited. A strictly abstract class is a class that everything is a pure virtual function, okay? A pure virtual function is a function that's declared as virtual and not defined, okay? It's a function that's declared as virtual but not defined. Okay, and so we can have an abstract base class called shape here. Shape has a virtual void function called draw. Okay, v equal to 0 just says it's a pure virtual, says it's not defined. Okay, in this class, this means that we cannot create, because this thing's purely virtual, we cannot create a class of shape. Okay, but then we can have the class circle, and the class circle defines this virtual function draw, okay, and it draws a circle. Class square defines the function draw, and it draws a square. This is similar to how Java's interfaces work, okay? You can think of this being exactly the same concept as Java's interfaces. So in Java, we might create an interface called shape, and we say it's got a draw function, and then Our circle class implements draw, and our square class also implements draw. Okay? No objects can be constructed from these abstract base classes. Yep.
Just a clarification.
Yep.
Does the equal to 0 part is like a flag for?
Yeah, it's a flag. If it equals 0, it's a flag to the compiler, saying this thing is purely virtual. Okay? Okay, so this is how these member functions work. Okay, so the virtual void draw equals 0 makes it a pure virtual. Okay, it means that it's an interface it has to be inherited from. Having something equal 0 makes that class not be able to be instantiated itself. Okay. If we go back and look at what we looked at earlier, for virtual void, net price function is still a virtual function, but it's not a pure virtual. It's just a virtual function. It creates the ability for it to be inherited, and it means it can be optional if it's implemented in the base class. Okay. The non-virtual function string ISBN is first of all non-virtual. Okay. It means that if a function ISBN gets inherited and it requires an implementation in the base class, okay, but it can be hidden. If you attempt to define your own ISBN function, and the base one isn't virtual, you just attempt to define your own, what you end up doing is you end up hiding the other one, okay? And this breaks everything to do with OO, and it's really bad, and we'll look at that, actually not on Thursday, we'll look at that in about 10 minutes' time, okay? So 3 different types of functions: pure virtual functions, and just your standard non-virtual functions. Okay, everyone's still with me? Because this is just going to get more difficult, okay? So if you get lost at some point, let me know, and we'll attempt to save it, okay? So that's the end of the introduction to OO, okay? Now we're going to keep going, okay? That was 27 slides. I now have 47 to go, okay? So we have, hopefully, to get through this by the end of the week, okay? We've got 47 slides to go to the end of the week. Okay, so we're going to keep looking at this memory, and we're going to keep looking at the structure of these objects in memory and how they all work. Okay? So keep in mind we've got these objects. Okay? So we've got this book object, we've got this discounted book object. Okay? We've got these objects in memory. Now, what is not stored in objects is the static data members, okay? Because they're not part of the object. Static data members are not part of an object. Static member functions are not part of an object, and they rely on static binding by the compiler at compile time. Non-virtual functions are not part of an object. They're statically bound at compile time. They're part of a class, not part of an object. Okay? So what's represented in an object? Well, for non-static data members, okay, so the fields for ints and the strings and all that sort of stuff is inside an object. Every object of book has a different string and has a different price object, a different double, okay? And for virtual functions, they're actually stored alongside an object, okay? So an object stores its virtual functions alongside it. So every instance of book and discounted book that I make has its virtual functions, okay? So the net price function stored alongside those objects, okay? So the non-virtuals, they weren't part of objects. The virtuals are part of objects, okay? Now, every polymorphic class, so every class that's got some virtuals, okay, also has a virtual table called a vtable, okay? The vtable contains the address to all the virtual functions, okay? It allows this dynamic binding to happen. Every object that is a polymorphic class, okay, has a hidden virtual pointer called a vpointer, okay, pointing to the beginning of its vtable, okay? And then the compiler stores the data members of this class in some predefined order, and we're going to make the assumption that these things are ordered from the base class through to the most derived class itself, okay? But that's not strictly true, but for the illustrations I'm going to use, we're going to say everything is in that order. And the compiler figures out this order automatically, okay? So it's going to be a little bit of hand waving, okay, but the important idea here is we've got these V-tables. And these V-tables help us work out at runtime what function to call when, okay? So let's look at three classes. I have a class book, I have a class discounted book, and I've got a class bulk discounted book, okay? In terms of memory, the book will be the first piece of that discounted book object, okay? So let me back up. We have these three classes. We then define a thing called DMB. Okay, I don't think it stands for dumb, but maybe it does. It's a bulk discounted book, okay? In memory, this structure of this class will first of all have the book pieces, the discounted book pieces, and then the bulk discounted book pieces. Okay, remember that's what it's going to look like. And like we said an hour ago, for data members in a sub-object are stored most likely in declaration order. And we're going to make this assumption that these things are stored in declaration order. This is what a V-table might look like. Okay, so we're going off that book example. We are going to come back to books. Okay, but this is what a V-table may look like in these inherited functions. We have class A, okay, so class A is our base class. It's got a function called voidf, which is virtual. We've also got a function called g, which is also virtual. Because this class has virtual functions, it therefore has a V-table. The V-table will have an entry for A to F, okay, and A to G, okay? Because it's a base class, it starts at that point. That's the V-table for class A. Class B, which inherits class A, okay, that also has a virtual void F, and now it's got a virtual void H. Okay, so F was overridden, okay, so for virtual void F was overwritten, but G stays the same, and now we've gained H. Our V-table now looks like this. Function F belongs to object B, but then the function G belongs to this base object A, and the function H belongs to this class B because it's defined it there. Okay? Class C inherits from class B. Class B, of course, inherits from class A. Okay? Remember our memory layout from a previous slide. This V-table is first of all going to have a virtual void F, but the B version. The B version, because even though F is declared up in A, it's then overwritten in B, it's not overwritten in C, so it gets the B version there, the void F, B version there. Okay. It gets A's version of G because G is defined there. It gets B's version of H because H is defined there, and then it gets the C there. So the virtual table for class C is like that. Anyone confused at this point? Can we see how this works? Okay, because this is how all the polymorphism works. Okay? So these V-tables and these V-pointers are initialized in constructors. Okay? So if we look back at book and discounted book, the V-table for book contains the net price function and the destructor. Okay? We'll come back to why the destructors are virtual, maybe on Thursday. We also, for discounted book, have the net price function, which is virtual, and the virtual destructor for the net book. Okay? If we go and create a discounted book, okay, we get a discounted book with this memory layout. the virtual pointer, which is pointing to the discounted books vtable, the ISBN number and the price, which is inherited from book, the max quantity and the discount, which is part of the discounted book object, sub-object. If we then create a pointer of book and assign it the address of the discounted book object, okay, it gets the pointer to this starting point of this object here. Okay, so the book object was assigned the pointer to this whole memory structure here, not for vtable. It gets assigned to that memory structure, that discounted book object in memory. Okay. Now, because this PB, it thinks it's a book, it can't access max quantity and discount. Okay, let's be very clear about this. It can't access max quantity and discount because it thinks it's a book, and a book doesn't have a max quantity and a discount. Okay. However, when there's the call to net price, so PB pointing to net price, because at the top of this structure here is the V pointer off to the vtable, and the V pointer for this disk book object is correctly pointing to the vtable for the discount book, it will always go and look at that vtable, regardless if it's being treated as a book or discounted book. Okay, so both the pointers for the discounted book and the pointers for the book object, so PB and PD, are both pointing to the same object in memory. The V pointer is only one V pointer because there's only one object in memory. Okay, so when I call PB pointing to net price and PD pointing to net price, they look up the same V table, therefore they get the same output, which is the net price function belonging to discounted book. Okay. So the dynamic binding says this: load the address of the net price from the vtable of a pointed to object and call the function at that address. That is what's going on. Everyone clear about it? Yep. Okay. Let's make this code more complex. So what we've got here is we're going to create a book object and a discounted book object. Okay, so I've got two objects in memory. Okay. The book object is this one on the left-hand side, V pointer, ISBN number, price, and it's the V pointer for that object is pointing off to that book there. The second discounted book is this box here, the object there. Okay. Now, I have a book pointer. And it's assigned the result of this if statement. So if x is greater than y, whatever x and y are, okay. If x is greater than y, then assign to a book pointer the address of b, else assign the address of db. So if x is 2 and y is 1, what does book get? If x is 2 and y is 1, what does the book pointer get for memory allocation of? A book. And if x is 1 and y is 2, what does book get for memory address of? It should be very obvious, yeah, okay. But if it's the other way around, so if x is 1 and y is 2, what does book get for memory address of? Discounted book. So on the next line, if I call P pointing to net price, if I call P pointing to net price, what comes out? So in the first situation of x actually being greater than y, it calls book B's net price function. In the second example, about x is less than y and therefore it's false, it gets to db, when I call this net price, I get for discounted books net price function being called. Now let's back this up a little bit. Let's go back to the compiling stage. So the static compiling stage. Okay? Book B, that's fine. Book DB, that's fine. pointer to a book, that's fine. Therefore, at the compiling stage, I'm assuming that I'm always going to be calling a book net prices function. So at the compilation stage, that's just assuming that this p pointing to net prices is the books function. Okay? At runtime, however, because this is dynamically bound to a different object in memory, and because of these v pointers, the function that it gets called is dynamically swapped out at runtime. Okay, so book and discounted book in particular is polymorphic. Actually, what this function call is polymorphic based on the values of x and y. Okay. So as the line below says, the compiler generates the same code. The compiler, in terms of machine code, generates the same code, which will call the appropriate function at runtime because these offsets, okay? So again, in memory, once this gets located down to machine code, everything gets put into jumps and stuff like that. Because this memory structure of these objects is the same, because these v pointers are always located in the same piece of memory, it works. Okay, so it loads the address of net price from the v table, okay, which is there, and it calls for appropriate function at that address. Okay? So what's going on here is compile time stuff, runtime stuff, and then load level, machine level stuff of figuring out at runtime what the correct function is to call. It's complex. Everyone clear on this so far? Yep. So this is basically the summary of what I just said in terms of machine code. It might be a push, a move, a call, and then some sort of cleanup up the stack. That's hand wavy. In reality, it's probably going to be doing a lot more than that. Okay, but you reduce this down to assembly, and it looks a bit like that. Now, let's talk about this object slicing a little bit more. Okay? Oops. Let's talk about this object slicing a little more. If we have a discounted book, DB, and we've got a book that's equal to DB, and we have this base book here and this discounted book here, okay? This causes us grief. So when we do the copy construction, the v point of a base now points to the v table for book. Okay, so the v pointer gets changed on that construction. The v pointer for book B is initialized in the copy constructor, and so these polymorphic calls are only achieved via pointers and references. Okay, so that's why if we do the copy, we actually get a solid book object, and its virtual tables get replaced, basically. Okay? So if you want a discounted book to think it's a book but still do the appropriate work, okay, and not have an object slicing problem, you need to make sure you use pointers or references. Okay? So these v-tables, okay, these v-tables are important because they help us with the polymorphism. They help us call the appropriate function depending on the type of our class. Okay? We are going to get to... Okay. We're not going to get all the way through this today, of course not. In this week's tutorial, there is a question about what is in some v-tables. Actually, I'm going to jump to it to show you, okay? Because this probably is a good point to highlight it. Okay, so in this week's tutorial, I've got some extra questions down here, okay? And one of the questions is, can everyone see that? I'm going to bring it up a little bit. What is not true about v-tables, okay? So let's take a look at what is true, okay? Because this is some important stuff to remember. So, how many v-tables is there for a class? One. There's one v-table per class, okay? So, book is a class, discounted book's a class, each of them have a singular v-table. Now, does a V-table contain an entry for destructor if the destructor is virtual? Yep, because the destructor is virtual, therefore it's in the V-table. What about a V-table contains an entry for a pure virtual function? Yep, because the pure virtual function is virtual, so yep. A V-table is never used for resolving a non-virtual function. Okay, I'm hearing false entry for that one. Okay, so let's think about this carefully. When is a V-table used? Sorry?
What if it's a virtual function, but then one of the base inherited classes makes it final? So then it's no longer a virtual function.
No, it's still inherited. It's still a virtual function. Okay, it's still a virtual function. You just can't override it anymore because it's set to be final. Okay, so when is a V-table used? Okay, so break this question down. When is a V-table used? Resolving a virtual function. Okay. So is a V-table used to resolve a non-virtual function? No. Why not? Because it's not virtual. But yeah, but why not? At the compiling level, what's different about it? So correct. So the non-virtual functions are part of a class. The virtual functions are part of an object. The virtual functions go into the V-table, and therefore the V-table is used to resolve a virtual function. A virtual table is never used to resolve a non-virtual function, okay? So therefore that's true, okay? So basically we've gone, yep, that's true, that's true, that's true, that's true. Okay, so obviously this next one must be false, but why? So a V-table may contain an entry for a constructor. A V-table may contain an entry for a constructor. Now this is what we're not going to address until Thursday, okay? But clearly through just our magical powers, we've gone, well, if A is true and B is true and C is true and D is true, obviously E is false because that's what the question's asking, okay? So why might a constructor not ever be allowed to be virtual? Why can't we have a virtual constructor? Pardon? Can't tell it compile time what the type will be. What do you mean by that? Yeah. Yeah. Basically that. Okay? A constructor goes and constructs an object. An object is not finished construction until the constructor returns. Constructor cannot be virtual because basically it doesn't make sense for it to be virtual. Your explanation was actually really decent, probably better than I can give. Okay? If we go all the way back to inheritance in terms of, say, a discounted book and a public book, the first thing that happens is our book's constructor gets called and constructs a book object, and then the discounted book's constructor gets called and constructs the remaining part of the discounted book. In doing so, what it does is it sits down and it puts the objects into that order like we've seen on the screens. Okay? So you can't have a virtual constructor. Now, again, this is different from Java. In Java, if you have an inherited constructor, what's the first thing that your inherited constructor should call? Super. Why should it call super? Because it constructs objects above. What happens if you don't call super? You have to do it manually. Okay? We don't have super the same in C++. We're just going to assume that super always gets called. So if you're coming from Java, the first thing you don't write it. The first thing that your constructor does is it calls super. Okay? The first thing that the constructor does is it goes and constructs the base objects first. Okay? So a constructor can never be virtual, and so a constructor can never be in the V-table. Okay? So a V-table never contains an entry for a constructor. Okay? So keep that in mind. I've just answered a tutorial question. This week's tutorial was short anyway. But break those sort of things down and thinking about that stuff. Okay, let's go back to whereabouts we were. Okay, so that's vtables, that's for object models. Okay, I'm going to attempt to make it through the next 4 slides and then we might be done. Okay, so we're going to talk about name hiding. We're going to talk about name hiding, and we're going to talk about okay, we're going to talk about these functions here. Okay, so we have this class fruit. We have this class fruit. We have this function virtual void eat float f, and it prints out that f and e was called. Okay, so if the eat function inside fruit gets called, you get some printout. We have the class apple, which inherits from fruit. It then creates this virtual void eat, takes an int I, and prints out AE. We then have an apple. Okay, we then have an apple, we say equals new apple. Okay. By the way, there's a memory leak in this program. We never delete for apple. Okay. Anyway, we create an apple object. Okay. We then create a pointer to a fruit object and assign it for memory address for an apple. Okay, this is fine. We then call f pointing to eat and pass it in 3.14 float. Okay, we then call a pointing to eat and we pass it in 3.14. What's the output? What's the output? So if we call f pointing to eat, okay, so this is a fruit. Let's resolve this. So this was a fruit object. We call eat. Is f and e or a and e going to be called? Remembering that the base type is an apple. Okay, so you're saying A of E. Okay, so we think that A and E is going to be printed out on that line. Yep. And the next line, A pointing to eat, so apple pointing to eat, 3.14F. You're going to say it's also A and E? Okay, so who thinks the output is going to be A and E? Oops, that shouldn't be an M there, but it's going to be A and E and A and E. Who thinks that's going to be the output? Oh, there's about 5 of you. Who doesn't know, by the way? Who thinks it's going to be something different? Why do you think it's going to be something different? Other than the title of the slide.
I thought it might be different because there'll be different virtual functions with one takes in a float, one takes in a int.
You're onto it. Yeah. So, okay, you figured out what the problem is, so what's the output?
A, F, E, F, E.
Sorry? What's the output? C?
The first one.
First one?
F, E, F, E.
F, E, F, E. Who thinks that's going to be the answer? Who previously thought it was going to be the other one and now thinks it's going to be that first one? Okay. Anyone think it's going to be B or C? B makes no sense. Why does B make no sense? B makes no sense. B is for answer. Okay, so let's see what happened. Okay, if pointing to eat, I'm hungry as well, I want lunch. If pointing to eat, okay, so it was fruit. That came in and that was a float, okay, and that function wasn't overwritten, so f of e gets printed out, okay. And then A came in and it looked up this V table here, okay, and basically this int I was a better match than this inherited class here, because what had happened was this eat function had been hidden. So even though this eat function here is also defined up here. What it done is that it had hidden it away because you got the types wrong. And so it had gone, well, I'm overwriting this function and this other one, well, I don't know what's going on there, so I've gone hidden it away. And so because it's hidden away, it came out to A and E. Does it still make no sense?
So it's actually turned about the parameters, it just sees some of the virtual fault eat and overwrites it.
Yeah. It just overwrote it. Yep.
So could you not overload a virtual function?
You can overload a virtual function. That's what we're going to get to. Okay. But the reality is, what you've done here is you've either tried to overload and you've got it wrong. Okay. Or what you've done is you've made a mistake. Okay. Let's just assume you've done one of the two. I don't care which one you've done, but either one of them is a mistake. And now you're getting the wrong output. Maybe you can argue for wrong output as the fact that doesn't make any sense, let alone the fact that it got the correct output. Okay? So, F's hidden in the base class, okay? Because if we look at overloading, overloading is when we have the same scope and the same name but different signatures, okay? So the return type's ignored. And then overriding is whereabouts we have the same name, same signatures, but different scope. Okay, so it's the difference between overloading and overriding. Okay? So we end up overloading something, and because it's in a different scope, we're going to hid it away. When we overrode it, which we should have done, we'd overloaded it. So overridden it. If we'd overridden it as a virtual, it would have done the right thing. Okay? So, two solutions to this problem. One, we bring through, if we intended that there was going to be two different functions, we intended that there was going to be two different functions, we can bring this fruits virtual void eat into scope. We can bring this fruits virtual void eat into scope by using virtual void each at that point in the correct scoping place, and it brings that up into the correct scope, and the resolution works as it should. That is one solution to the problem. Okay? Now, we should, as we state up top here, avoid name hiding if possible. Avoid these types of errors if possible. Okay? But there is a solution if you wanted it like that, and we do it like that. And we've seen this before, previously on the semester. Where did we see this before? Anyone remember? We saw this in the second or third week. Yeah, it's to do with namespaces. Yeah, it very much is to do with namespaces. We saw this in the second or third week. So why do we just not have, say, for instance, using namespace standard? Pollutes the global namespace, okay? Because it brings all the stuff in and pollutes that namespace there. And that's roughly where we saw it at the start of the semester, only we saw it in a particular place whereabouts where we had the sort function. And we had a specialized sort for when we were using pointers. And so what we had is we had using standard sort sitting in there. We had a special overridden function as well, and so when sort got called, it did the parameter, it did the argument deduction logic. So this was actually the Thursday of week 2. We did this, and we did the argument deduction logic and worked out if it should call the standard sort function or if it should call our specialized function, because it had brought the things into the same scope. That's basically the same thing that's going on here. So we're bringing forward that fruit eat function into the correct scope. Okay? So that's one way of doing it. The second way of doing it is to use the word override. So I've lost whoever asked this question before. Maybe it has disappeared. Has Simon disappeared? Yeah. Okay. So the person who has left, who asked a question almost 2 hours ago, this is the answer to the question. Okay? How do we tell something that needs to be overridden and enforce it? Okay? Well, if we say that virtual void eat overrides something, so we say the word override here, we're telling the compiler, hey, tell us if we stuff up. And what's happening here is this override is saying, well, actually, you attempted to override a function called eat that takes an int I, and there's no function called int I that I was meant to have overridden. So it comes in and says, this thing is marked as being an override, but doesn't override anything, and therefore it doesn't compile. Okay? So using word override allows you to basically help in the debugging of your code. Okay? So that's quite powerful. Okay, so I'm going to stop at this point. On Thursday, we're going to look at briefly at covariance and quantivariance. I've taken a lot of those slides out because they're more theoretical stuff that isn't in the exam. We're going to look further at initialization and destruction. Then we're going to look at an object-oriented stack interface. So I'll see you on Thursday.